This is actually a really good time to take a look at why we might want to study trigonometry in the first place. There are actually a lot of applications for trigonometry. We'll just be taking a look at a few of them here. The first time I ever even heard of trigonometry was when my father, who used to have a private pilot's license, talked about having to make a flight plan and using trigonometry in his calculations for bearing and so forth. We're not going to be talking about that one here, but we are going to be talking about a couple of other instances. One example is that while it's possible to measure the height of some things, other things, like mountains, are a little harder to measure the height without some kind of tool. If you have some idea of how far away from a mountain you might be, let's say 3 miles, and you know what the angle is when you're looking at it, we call this the angle of elevation. And let's say that's 3 degrees. Well, let's use a different number. Let's call it 2 degrees. We know the angle of elevation to the top of the mountain. With that information, you can find the height of the mountain. Here's another example. Say you're in a building and you're at a window, I'm going to say 300 feet up from the ground. If there's another building across the street, let's make sure it's a different height. You can tell from your vantage point what the angle of elevation is. Let's call that 45 degrees. And what the angle of declination is, we'll call that 38 degrees. And you also know how far away you are, then you can tell how tall this other building is. There are a lot of other examples as well, but notice in both of those cases, and this will always be true, that we knew some things about angles and distances, but not everything. So we're going to start this video, this section, by talking about solving a right triangle. What that means is, given any right triangle, and given some information about some of the angles or sides, lengths of sides in that right triangle, I can find all of the others. Some things are easy to find and others are a little more challenging. Let's say that we know the angle of this angle of our triangle is 40 degrees. Well, since this one's 40 and this one's 90, and since all of the angles in a triangle have to add up to 180 degrees, this one here, we'll call it theta, has to meet this criteria. This is 130 degrees, so theta has to equal 50 degrees. The other thing you could do here is say, well, since I know this one's 90, these two have to add up to 90. Since this one's 40, this one has to be 50. Notice that we're just dealing with right triangles here. So as long as I give you one of the other angles, it's usually pretty easy to find the other. If it's 12.7 degrees, the arithmetic might be just a little bit more challenging, but you're still just doing basic subtraction. Another thing that's easy to find is the length of a third side if you know two sides. If I know this side is 3 and this side is 7, I can find this side using the Pythagorean theorem. That side is just the square root of 3 squared plus 7 squared, which is the square root of 9 plus 49, which is the square root of 58. Easy. The problem arises when you don't have two sides, so you can find the third, or you don't have one of the angles, so that you can find with a 90-degree angle, so that you can find the third. In some cases, you have different pieces of information. Let's go back to a generic triangle. Take a look at theta here. We know some things about sines and cosines now, so we can say that the sine of theta is equal to opposite over hypotenuse. A little bit of algebra gives us that h, hypotenuse, times the sine of theta equals the opposite. In other words, I can write the length of this side is equal to the hypotenuse times the sine of this theta, the sine of this angle. So if I know this angle and I know the hypotenuse, I can find this side. I can do the same thing with cosine. Now, I'm going to change this just a little bit because as we go forward, the notation that I'm using here is not what's used conventionally, and so I want to introduce the conventional notation now, and then I'll explain why we use that notation later on. I'm going to change my H to an R. If you've seen this before, you might recognize that R stands for radius here. If I multiply both sides of this equation now by R, I get the opposite side is equal to, I forgot to put my R in here, the opposite side is equal to the length of the hypotenuse, this R, times the sine of this angle. So again, if I know these two values, I can find the opposite side. It's also more common to label the sides A and B rather than opposite and adjacent O and A. So I'll use little a and b. If I can get my pen to work. And then I'll change this O for opposite to little a. So again, we started with sine of theta. Sine of theta equals opposite over hypotenuse. Well, that's just called A and R now in this diagram. Multiplying both sides of this equation by R gives me A, the opposite side, equals R sine theta. If I do the same thing for cosine, I get that the cosine of theta is equal to the adjacent, which I've now labeled B, adjacent over hypotenuse. Multiplying both sides of that by R gives me B equals R cosine theta. The adjacent side is equal to R times the cosine of the angle, the hypotenuse times the cosine of the angle. So these are kind of interesting little shortcuts, but they're going to come in handy when we try to solve a triangle if we don't have just two angles out of the three or two sides out of the three. Let's take a look at an example. Here we've been asked to solve the triangle, and the triangle is given below here. And what that means is that given this angle and this side length, I've been asked to find this other angle and these other two sides. Well, the angle's pretty easy. All I need to do is figure out how pi over 6 plus 90 degrees plus this other unknown angle, the one I'm looking for, equals 180 degrees. Well, one thing I'll point out here is that you can do all of your work in degrees or all of your work in radians, but you can't mix and match. We're either going to need to convert this to degrees and then figure out what this angle is from there, or convert these other ones to radians. I'll give you a hint. Although it would be easier to convert one angle to degrees than two angles to radians, we're gonna do it the other way around. We're going to convert these two to radians and give our answer in radians. And that's because in the diagram, the only given angle is given in radians. So clearly the author is expecting the answer to be in radians. So let's convert these to radians and go from there. Pi over 6 is already in radians. 90 degrees the degrees can just go with it, is pi over 2. So I have pi over 6 plus pi over 2 plus the angle phi is equal to, well, this one should be easy, pi. All right, now how do you add fractions? We get a common denominator. So I'm going to multiply this angle here, this fraction, by 3 over 3. That'll give me pi over 6 plus 3 pi over 6 plus phi equals pi. That's 4 pi over 6 plus phi equals pi. Now, if I subtract pi from both sides and subtract phi from both sides, then I'll end up with phi is equal to, and I'll have an angle, but they'll be negative. So instead of that, I'm going to subtract 4 pi over 6 from both sides. So subtract this 4 pi over 6 from both sides. And that leaves me with phi equals whatever pi minus 4 pi over 6 is. Well, again, I'm working with a fraction here. So what if I change this to 6 pi over 6? That gives me phi is equal to 2 pi over 6 or pi over 3. So that means that this angle here is equal to pi over 3. Well, that's my answer for the angle, and I need to go back in and figure out what the other two sides are. I've only found the third angle, but if you're interested, you can figure out what that angle is in degrees simply by doing the other conversion. You would take pi over 3 and multiply it by 180 divided by pi, this time, 180 degrees divided by pi, because this time we want the pi's to cancel. And we're left with 180 degrees divided by 3, which is 60 degrees. Well, I don't know if you remember, but the pi over 6 with the 6 in the denominator was the 30-degree angle, and the pi over 3 with the 3 in the denominator was the 60-degree angle. So that actually makes sense. This is actually just a 30, 60, 90 triangle, but I've labeled it in radians instead of in degrees. Okay, now that we've found the third angle, it's down to us to find the other two sides. Now, we could have done the other two sides first if we'd wanted to. We have these two new formulas here. A equals r sine theta, and B equals r cosine theta. When you use these formulas, you have to be careful that you know what A and B are. It doesn't really matter. Remember that we said A, in the case of this triangle, A was the side opposite the angle, and B was the side adjacent to the angle. But we're not going to worry about the labels here. We're going to use instead the idea of the trigonometry involved. So we're going to say here that the cosine of pi over 6 equals the adjacent side, which is B, over 7. And the sine of pi over 6 equals the opposite side, which is A, over 7. That way, if I had labeled these K and P or some other weird numbers, weird letters, you would still be able to figure out what the ratio was based on your knowledge of trigonometry, not based on some randomly memorized formula. All right, now we'll multiply both sides by 7. Here we get 7 times cosine pi over 6 equals my side B. And here I get 7 times the sine of pi over 6 equals my side A. That's going to be 7 times a number equals B, and 7 times a different number equals A. In the last video, we made a chart showing the sine, cosine, tangent, cotangent, secant, and cosecant of special angles, and pi over 6 was one of those special angles. So if you look at that chart, you'll see that the sine of pi over 6, which is the sine of 30 degrees, is 1/2. And the cosine of pi over 6, which is the cosine of 30 degrees, is the square root of 3 over 2. So B is equal to 7 root 3 over 2, and A is equal to 7/2. Those are the lengths of those two sides. B is 7 root 3 over 2, and A is just 7/2. So I now also have the answers to those two pieces. I was given 3 pieces of information. The fact that this is a right triangle means that that angle is 90 degrees, or pi. This angle was given to me as pi over 6, and I was given the length of the hypotenuse. And I have found the other 3 pieces of information. So I have solved this triangle. All right, now let's take a look at an example in an application. In the next problem, we're going to be given a scenario that we have to interpret. Once we've interpreted it, we'll be able to solve the triangle or solve part of the triangle to figure out what the answer to the problem is. Okay, let's say you want to figure out how tall this mountain is. That's you standing with a pair of skis. For some reason or through some means, you know that the distance from you to the center of the mountain is 39 miles. And as you look up at the mountain, look up at the top of it, you can measure that the angle of inclination is 3 degrees. With that information, you can figure out what the height of the mountain is. Let's see what we've got here. If we treat the mountain as though it's a vertical line, like this height line over here, then we have an opposite side from our angle. We have an opposite side here, and we have an adjacent side here. Which of the trigonometric ratios deals with an opposite and an adjacent? There are two. There's tangent, which is opposite over adjacent, and there's cotangent, which is adjacent over opposite. It's usually easier to use the primary functions, sine, cosine, or tangent, so we're going to go with that. And we know from this that the tangent of 3 degrees is going to be the opposite side, which is the height, over the adjacent side, which is 39. So I have h over 39. Now, if I multiply both the sides of this equation by 39, I get that the height of the mountain is 39 times the tangent of 3 degrees. And that's my answer. I can figure out what the tangent of 3 degrees is, or I can approximate it, and I'll just use a calculator for that. But this is the exact value. Let's see if we can figure out what it is approximately so that we have an actual answer here. I'm going to use a calculator, and when I type in tan 3, close the parentheses, and hit enter, I get negative 0.143. Well, that's a problem. How can a positive height divided by a positive distance be a negative number? And the issue here is that my calculator is in radian mode. The problem is in degrees. So I first need to change my calculator so that it's in degree mode. And then when I type tan 3, I get 0.0524. So that's actually the correct answer. I'm going to erase this one, the correct intermediate answer, 0.0524. I want to keep as many decimal places as I can for as long as I can. So although I've only recorded this much of the decimal the calculator spit out, I'm going to leave the entire decimal, which is what, 9 or 10 digits? I'm going to leave that in the calculator, and I'm going to press times 39. It'll pull up the previous answer, giving me all of that decimal accuracy, and then times 39 gives me 2.0439. So the height of the mountain is approximately 2.0439. Now the question we have to ask ourselves now is 2.0439 what? If you look around at the scenario, or if you reread the description, which I didn't write out here, if you reread the description of the problem, you'll see that the only measurement that's actually given, the only linear measurement that's given, is in miles. So I'm dealing with 39 miles here and here and here. So the answer is 2.0439 miles. The mountain is about 2 miles tall. Now mountains are usually measured in feet. So if 1 mile, and I'll just give you the conversion here, is 5,280 feet. If we want to know what 2.0439 miles is, all we have to do is multiply both sides of this equality by 2.0439. In other words, we have to multiply that 2.0439 by 5280. Again, I've only recorded part of what the calculator spit out for me. My calculator actually says it's 0.0439033392 miles. So I'm going to leave that on the screen, hit times again, and then type in the 5280. I get that the height of the mountain is still approximate, but it's much more accurate than if I just use 2 or 3 or 4 decimal places. Approximately 10,791.81 feet. Actually, I would just say 10,792 feet. That's close enough for measuring a mountain. Now, I actually got this problem by thinking about Mount Baker. When I looked it up, I was told that Mount Baker was 10,786 feet tall. I used that information and other information that I found online that it was 39 miles between Western Washington University and Mount Baker. They didn't have a measurement from Whatcom Community College. But from Western to Mount Baker, as the crow flies, is apparently 39 miles. Now, I had to take their word for it, but that's where I got the information, that the height of the mountain and the distance away from it. I used trigonometry actually kind of in reverse to figure out that the angle of elevation here would be about 2.99, what was it, 2.9984 degrees. So I rounded that up to 3. Now, interestingly enough, rounding that up just a tiny little bit made my mountain actually taller than the mountain really was. It was 10,786 feet, not 10,792 feet. So rounding up just less than a tenth of a degree made my mountain actually, 6 feet taller than it actually was. So tiny little rounding error here introduced a considerable amount of extra height on the mountain. I say all of that just to give you a couple of things to think about. One is that I can figure out what this angle is if I know this height and this distance. Now we need to use trig in reverse, and we haven't learned how to do that yet, but we will. That's another way we can use trigonometry. The other thing is just how little rounding error it takes to make a pretty big difference in the answer. Just something to keep in mind. You don't need to worry about it. If I were to give you this problem on a quiz or an exam, this would be the answer that I would accept. This answer or this close approximation. These are good enough for this problem. I've given you round numbers here and here to work with. Okay, let's take a look at another example. Before we do, let me just remind you about this terminology that I've been using. This is called the angle of inclination or the angle of elevation. In the United States, most of the time you hear angle of elevation, but it's not uncommon to hear it called the angle of inclination as well. In the next problem, we're going to be looking at the angle of inclination or the angle of elevation and the angle of declination or the angle of depression. And I'll explain those terms when we look at the next example. Okay, this time you're at the top of a cliff and you happen to know that the cliff is 250 feet high. And you notice down here on this ship that there's somebody waving for help. And you radio it in, but they ask you, how far away is the boat? How far away is the ship from the cliff? How far out to sea is it? So what we want to find out is this distance here. The only other piece of information you can obtain is the angle between you and the ship. Now, it'd be nice to know what this angle was, but when we talk about angles of depression, what we're talking about is this angle right here. As you look out to sea, you're standing here and you're looking straight out on a horizontal. The angle of depression is the angle down from that horizontal. This is the angle of depression. So if you can tell that the angle of depression is 10 degrees, then you can also figure out what the angle left over is. But be careful that you use if you're given the angle of depression is 10 degrees, don't label this one 10 degrees because that's not what it means. Now it's interesting to note, based on some geometry, that we can either use the fact that this is approximately a right angle, and the fact that three angles must add up to 180 degrees, we can figure out what this angle is based on this angle by subtracting 10 from 90. That'll give me 80 degrees here. If this is 80 and these two have to add up to 90, then this is also 10 degrees. We could also, though, have got there straight or more directly by noticing that these are effectively parallel lines and this line traverses or crosses those two parallel lines. So these are what we call opposite interior angles, and that means that this is also 10 degrees. Now, however you get there is fine, but that is another way to solve that problem. So we have that that's 10 degrees, and we also know that this angle here is 80 degrees. I don't know if we're going to need that yet. What we're interested in is, what is this distance here? We now have all three of the angles, but only one of the sides, and we're looking for the other side. So from this angle here, we can either say that the tangent is opposite over adjacent, or from this angle here, we can say that the tangent is opposite over adjacent. Let's set those both up so we can see which one might be easier to work with. I'm going to call this angle theta and this angle phi. The angle theta has a tangent that is opposite, which is the d, over adjacent, which is 250. The angle phi has a tangent that is 250 over its adjacent, which is d. Now, to solve this problem, I want to multiply both sides by 250, and that gives me 250 times the tangent of theta is equal to the distance. To solve this one, I need to multiply both sides by d to clear the fraction, but that gives me d times the tangent of phi equals 250. That's a little harder to solve because I know phi, I know the angle here, the phi, I don't know, pho, phum, you pick. I've heard it pronounced two different ways, phi and phi. I tend to pronounce it phi. For some reason, I've been calling it phi so far in these videos. But if I know phi, I can stick it in. Let me rewrite it instead of erasing. I can stick that in there now. Phi, we said, was 10 degrees. Solving this for d is going to be difficult. Not impossible, but difficult. I'm going to have to divide both sides by tangent of 10. Let's go ahead and write that out too. D equals 250 divided by the tangent of 10 degrees. This one, on the other hand, is all ready to go, right? I know what theta is, so I can rewrite this as 250 times the tangent of 80 degrees, and that will give me the distance. Either one is correct, but in this case, I had to take an extra step. Doesn't matter if you set it up this way, and then you find yourself having to take an extra step to solve for d, that's fine. It's not worth going back and redoing it because you've already taken those steps. But if you take just a moment to notice that if you have the opposite as the unknown side, that means using this angle here, then multiplying by 250 is the only step you have to do before you can actually solve. So it doesn't really matter which one you use. In this case, I'm going to need the tangent of 80. My calculator is already in degrees from the previous problem. So I'll go tangent of 80, and that's 5.671. So this is 250 times 5.671 equals d. And again, I'm going to leave a much more accurate estimate in the calculator. I'm just recording 5.671. It's actually several more digits, several more decimal places. But I'm going to multiply that now just by saying times 250, and then the calculator pulls in the entire decimal rather than the rounded value. And I get 1417.8205. 8205. And I'll come back and talk about units in just a minute. This one here, now that it's set up, I can do that as 250 divided by tan 10 degrees, and I get 1417.8205. So I get the same answer with either one of these. I like this one better just because it was one less step, but if you end up setting it up this way, you get the same answer, so it really doesn't matter. All right, let's take a look around. We have degrees, 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 and feet. So since what I'm looking at is this linear distance, it must be in feet. So my unit is feet. And this is my answer to that problem. This is what we call the angle of depression, mostly in the US, but often you'll hear it called the angle of declination. You had inclination in the other problem, and here we have declination, decline, or the angle of decline even, the angle of incline and the angle of decline, but usually it's the angle of inclination and the angle of declination. But this is the one that's more commonly used in the US, so that's probably the one you'll hear the most. Let's take a look at a problem that uses both. I'm just going to do question number 60 in your textbook. Okay, here's our question. A woman standing on a hill sees a flagpole that she knows is 60 feet tall. The angle of depression to the bottom of the pole is 14 degrees, and the angle of elevation to the top of the pole is 18 degrees. Find her distance from the pole. Now, your textbook already has a diagram, but it's a really good idea to draw a diagram if you don't have one. So let's go ahead and make our own diagram here. We're told the woman is on a hill, so I will put her here. And she is looking at this pole, and if she looks down to the bottom of the pole, actually I want to do that slightly differently. If she looks down to the bottom of the pole, they tell us the angle of depression is 14 degrees. And if she looks at the top of the pole, the angle of elevation is 18 degrees. But both the angle of depression and the angle of elevation are taken from the horizontal. So we need this horizontal line here, and then I'll use different letters. I think I'll use theta for the angle of elevation. That's a symbol that means angle, by the way. And I'll use phi, for the angle of depression. So that's here. Now in the previous problem, we needed not this angle here, but the angle that was left over underneath, what was left of 90 degrees. In this case, this is actually what we need. The angle of depression is the angle down from the horizontal, and that's what we want. All right, so we're told that this is 18 degrees, and this one is 14 degrees. And we're asked to find her distance from the pole. We're asked to find this distance here. Now, the other piece of information that I haven't included yet is that the fact that the pole is 60 feet tall. So this entire thing is 60 feet. That height there is 60 feet. Now this is kind of a tricky problem because I have a potential opposite over adjacent with this 18 degrees. I have an opposite here and an adjacent. That's a tangent. And I have another opposite over adjacent with this 14 degrees. The problem is I don't know what this part of the pole is or this part of the pole is, and that's what I need for my opposite and my adjacent, or my opposites. So if I label, actually I'll use, instead of using a highlighter, I'm going to use a pen. I'll use a slightly thicker pen than I've been using. If the top of the pole is this blue color and the bottom is this kind of lurid pink. Sorry about that. My tools are fairly limited in this software. Then if I could figure out what this pink was, then I would just have opposite over adjacent, and I would be able to figure out what the adjacent was from that using a little bit of algebra. So I don't know what these two measurements are, but I know they add up to 60 feet. So let's see what we do know. I like these kinds of problems because it's sort of like doing a puzzle. let's call this distance A. Oops, I have too thick of a pen now for that. Let's make that a little bit easier to read. There we go. I'll call this distance A and this distance B, or that height, that partial height A and the other partial height B. And I know that, and I also probably should point out this yellow highlighted dotted line, that's the distance I'm looking for. Your textbook labels it X, so I'll do the same just for convenience. All right, so I know that the tangent of 18 degrees is going to be equal to opposite, which is A, over X. That's my adjacent. I also know that the tangent of 14 degrees is going to be that one's opposite, which is B, over its adjacent, which is also X. And at this point, I have several different things I could do. One is to figure out what these tangent values are, but I'm not going to do that yet because this, in its current form, this is the exact value. And if I can wait until the very last minute to work out what those values are, then I'll have the most accuracy in my answer. Something else I could do is solve both of these for X. Since it's the same distance, it's actually the same line. I could solve both of these for X and set them equal to each other. If I did that, I would get A over tangent of 18 is equal to B over tangent of 14. And that doesn't really help me too much yet because I still don't know what A and B are. But whether I do that first or whether I leave them as they currently are and try to figure out how to relate A and B, doesn't really matter if I do that, do this step first or do the thing I'm about to do first. The thing I need here is what are A and B, or at least what are they in relation to each other? And what they are in relation to each other is that they add up to 60 feet. So I have this information, which I can think of or rewrite as A equals 60 minus B. If that's the case, I can replace this A in either of these forms with 60 minus B. Doesn't want to erase there. 60 minus B. Of course, I could also have replaced B with 60 minus A, but don't do both. So now I have a proportion, and I can solve this by cross multiplying. I have B times the tangent of 18 degrees is equal to 60 minus B times the tangent of 14 degrees. And if I distribute this value, the tangent of 14, I get B, the tangent of 18 degrees, equals 60 times the tangent of 14 degrees minus B times the tangent of 14 degrees. And now I'm going to add this quantity to both sides. So I get B times the tangent of 18 degrees plus B times the tangent of 14 degrees equals 60 times the tangent of 14 degrees. And then I'll factor out the B. Tangent of 18 plus the tangent of 14. So now all I have to do to isolate B is divide both sides by this quantity. I'm going to do that over here, but that means I have to erase this little note that I made a minute ago. Put this over here, and I have B is equal to 60 times the tangent of 14 degrees divided by the tangent of 18 plus the tangent of 14. And now I can put all of this into my calculator kind of all at once and get a value for B. So let me do that, but I'll do it off screen. B is approximately equal to 26.051. Actually have 0509, so I'll do that. And that tells me what this height here is. To find out what A is, I would need to subtract 26.0509 from 60. Do I need to do that? Well, what am I looking for? I'm looking for x. And I can take either one of these now, multiply by x, and divide by the tangent. So let's do this. This one's simpler. I'm using this one because it has just a b, not a 60 minus b. If I multiply both sides by x and divide by tangent of 14, I get x is equal to b over the tangent of 14 degrees. Since x is what I'm looking for, I don't really care what a is. I'm looking for x. So if I solve this equation now, where I use the value of b that I got and that I still have in my calculator, see, I would have to call that 26.1, but I've recorded 26.1, I've recorded 26.0509, but I'm actually going to use 26.05091878 and more because that's what's already in my calculator. I'm going to take the number that's already showing on my calculator and divide by the tangent of 14, and that gives me 104. It's still an approximation, but it's 104.4845. And that's actually 4845284 and more, but that's close enough. So what I was asked for was the distance from the pole. I labeled that x, and now I have found x. So this is my answer to the question, accurate to 4 decimal places. If I'd been asked for more decimal places, I could give more. I can't give an exact value here because I don't have a way to find the tangent of 14 degrees. The only way I can find an exact value for a tangent is if I use the angles in degrees. It would be 30, 45, or 60. Those are the only ones I have access to exact values for. For the others, I have to use a calculator. But that's often the case with an application anyway. All right, that's going to do it for this video. There are always lots of other applications we could look at, but there is only so much we can do in the amount of time that we have to work together. I've tried to give you examples of an application using an angle of elevation, one using an angle of depression, and one that uses both.